Hello everyone, and for coming. Today I have the Dr. Seth Hutchinson. Thank you, Dr. Seth, for accepting our invitation. Dr. Seth, can you hear me?
Yes, I'm sorry. Yeah, I do hear you.
Oh, okay.
Hello, Seth. How are you?
Hi, Rafael. Good to see you. I'm all right.
Thank you very much for accepting our invitation.
You're
It's
welcome.
it's a pleasure to have you here. And we know you are very busy, and we really appreciate your time. Thank you very much. Please go ahead. You can share your screen, and it's your talk.
All right. Thanks for the invitation. I'm sorry that I'm in Atlanta and not in Guanajuato. I hope sometime before too long we can fix that, and I can get myself down there. Let me share my screen. There. Perfect. All right. So first of all, thanks for this invitation. I think it's my second talk at the CMAT to be given virtually. So the third talk I give at CMAT, I promise you, will be in person. So Rafael, the next time I'm coming if you invite me. So be careful with the invitation. So I'm going to talk about, give me a second to hide some of this stuff because I can't see the screen very well. There, put that down there. Nope. Go. And I should be able to hide this as well. Oh, wow. Sorry. That was too fast. All right. So what's the place for model-based methods in robotics? That's the theme of my talk today. And what you see here, it's a photograph that I found on the internet. It's from Life magazine back in the 60s. These guys were working for NASA, at the time, planning how to get rockets to take people to the moon, right? And everything that was done in those days, completely model-based, right? And what you see on the board are the equations that define the various models that the people are using. And today, you have situations where companies with a lot of money buy a lot of robots and enormous collections of computers and basically collect data, collect a lot of data over a long period of time and use learning methods to decide, how robots should behave in the world. Right? So you have two very different kinds of approaches. And the machine learning stuff that people are doing now, a lot of problems that have been in the robotics community since the beginning of robotics look like they're starting to be solved by machine learning methods. The animated GIF that you see here, it's a grasping problem, right? The robot is learning how to grasp things. It's a variation on the bin picking problem. Dexterous manipulation is something that learning folks are starting to work on. And you can find videos on the internet now of multi-fingered robots that are, manipulating things with their hands, with their multiple fingers. A lot of learning work, data-driven in legged locomotion, especially for quadrupeds. Computer vision has really done well with machine learning and object recognition, scene understanding, and there are more. Okay, so some of the most successful approaches that are happening right now in robotics are happening by combining deep learning with reinforcement learning, which is known as deep RL or deep reinforcement learning. And that's basically a model-free method based on what you acquire from data. And that raises the question, is there still a place for model-based approaches in robotics? And the first time this question was raised to me in a serious way, I think, I was visiting a university it's been almost a year ago now, and I was in the laboratory of some young guy, and the young guy asked me, he said, I don't want to offend you, but can I just ask you, you're not doing any kind of machine learning stuff at all. Do you really think you're going to be able to stay relevant? And he asked it in a slightly nicer way, but the question was pretty, it caught my attention, right? It was a question I thought I better think about this. I don't want to become the old dinosaur who's completely out of touch with all the stuff that's happening. What's the motivation for me to continue doing these kinds of things, right? And so preliminary ideas that come to your mind pretty quickly, I think, when you start thinking about using data-driven approaches, deep learning style methods, is that there are some difficulties with those methods, right? So first of all, collecting the data is not always easy. Quite often it's expensive. And by expensive, I mean actual money has to be spent, right? You have to pay people. You have to buy robots. If you're doing the robot farm with a lot of robot arms doing the same things over and over again, then the cost of 18 KUKA robots is a pretty significant cost. It takes a lot of time to collect the data, and it can be dangerous, particularly dangerous for the robot itself, because if the robot fails in some kind of catastrophic way during a learning episode, you may break pieces of the robot that are expensive to replace. Also, it costs time. Every time you break the robot, you incur the cost of time to fix the robot. And I'll give some specific examples of that later in the talk. You immediately think, well, I'll do a bunch of learning in simulation, and then I'll port the stuff that I learned onto my real robot system. And that's not always possible. Complex dynamics can be, very heavy in terms of computation. And so it's difficult to do really large scale data analysis if the computation for any example is very heavy. It's hard to model non-deterministic effects very well in simulation. And there's this thing called the sim to real gap, which is the distance between what happens in simulation and what happens in the real world. And that's a real thing that, there are plenty of papers now that have that word, sim to real gap, in the title, right? This is the thing the machine learning folks are trying to deal with. Finally, even if you have the money and the time, choosing the right data isn't always easy. And this, the name of the problem that goes with this is out of distribution errors or out of distribution problems. And the idea here is you have a robot that learns a bunch of stuff, goes out into the world and starts doing things, and it encounters situations that are nothing like what it saw during its training. Right. And so the word distribution is used because usually we talk probabilistically about the set of examples that you'll feed to the robot. And so we're talking about, probability distributions over prior worlds and over problem sets that you might obtain. And if you're not sampling from the distribution that your real world problems will come from, then you won't learn the right kinds of things. So there are advantages of model-based methods in addition to disadvantages of data-driven methods. Model-based methods admit provable performance guarantees. Admittedly, the performance guarantees that you get are with respect to the models that you use. Right? So if your models are horrible, your performance guarantees may not mean very much, but you can at least prove things mathematically about the performance of your mathematical model. And to the extent that the model captures the relevant behavior of the system, you'll have good insights about the performance that you can expect. Second, even reasonably good models do really well if you wrap a closed loop controller around the model, right? So reasonable models plus closed loop control often will give you performance that is quite good. And then the last thing is, if you're using models, you can do optimization, where you have some kind of system model that you can either use as a black box simulator going forward, or you can get inside the model, right, and see what's really happening and optimize individual pieces. And in the talk today, for the rest of the talk, basically what I'm going to do is I'm going to look at some specific systems that I've been working on and my group has worked on over the last few years from the perspective of model versus data, right? And the sort of pros and cons of those kinds of approaches for the specific kinds of problems and systems that we've been looking at. Right? So that's the way it's going to go. And depending on how much time we have, I'll do 3 or 4 different systems, and I'll try to stop try to find a watch. Yeah, I'll try to stop by 2:30 or so, or 1:30 your time. Here's the first one. This work I did with some colleagues at the University of Illinois. I left there in 2018. But the work kind of continued and it finally wrapped up around 2019 or 2020. Right, so it's a biologically inspired bat robot. And what you see on the left is a real bat, and what you see on the right is the bat robot flying around in the lab at the Coordinated Science Lab at the University of Illinois. So if you're going to ask about data-driven methods for particular robot systems, the first question to ask is, what is the data that you might be able to have, right? What kind of data is even available to you? And with the Bat Robot project, basically there are 3 kinds of data that we had. The first kind, which you see in the figure on the left, was motion captured data from a real animal flying in a wind tunnel, right? And everything that I say about real animals in wind tunnels is because of a collaboration with folks at Brown University, Kenny Breuer and Sharon Schwartz. And you'll see more of the stuff out of their lab as I go through these slides. So you can get that kind of data. Secondly, you can take your robot and fly the robot in some sort of motion capture environment and measure a lot of stuff. And that's what the middle scene is showing you, right? This is a laboratory that's got a bunch of Vicon motion cap cameras around the side so that we can measure things very precisely. And then the last kind of data we had access to, you can take the robot and strap it onto a force torque sensor and measure what kinds of local forces and torques you can get by flapping the wings, right? So this is not really what's happening during flight. It's just a question about what kinds of forces are available to the robot at flight time. Excuse me. So let's start with the biological studies. Right, the biological bat, a cartoon is shown on the left superimposed over a picture of a real bat so that you can see the skeletons and the joints in the skeletons and the degrees of freedom. And the biological bat, it's complicated. There are more than 40 degrees of freedom. Some are active, some are passive, some are coupled. Some of the joints are revolute, some of the joints are ball and socket joints. And it's way too complex to ever try and replicate this in a robotic mechanism. Right? If you have 40 degrees of freedom and you want to actuate, let's say you want to actuate 20 degrees of freedom, it means 20 little motors. And at this moment, your bat robot is too heavy to fly, right? And you could say, well, just make the bat robot bigger and it can carry a heavy payload. But this doesn't work, right? Flapping flight only works up to a certain size. When animals become too big, flapping flight doesn't work for them anymore. It's the reason we don't have airplanes that flap their wings, right? It's this aerodynamic stuff that has to do with Reynolds numbers. And really, if you want to have flapping flight be successful, smaller is better, right? Hummingbirds, their wings flap so much faster than falcons, which flap their wings faster than condors, etc. Right? So the bigger the animal, the slower the flapping speed, and the less like flapping flight it is. So we're not going to build a bat robot that duplicates this kind of complexity. Right? One of the things that probably jumps out at you if you've done much work in robotics, and particularly if you've done any work with grasping and multi-fingered hands, is that the skeleton of that bat is a lot like the skeleton of your arm from your shoulder to your fingertips. Right, so you have 3 degrees of freedom at the shoulder, then you have an elbow, and then this bat has basically 3 fingers instead of 5. So topologically, the skeletal structure of this bat is very similar to the topological structure of the human skeleton from arm to fingers. And that reminds roboticists of this concept of synergies that have been very popular in the grasping community. Right? So if you think about grasping an object with your own hand, one of the things that you'll notice if you start grabbing different things is there aren't that many interesting things that you do. You know, you grab a bottle like this, and it's a small degree of freedom motion, even though there are a lot of degrees of freedom involved in the action, right? Basically, closing my fingers is a one-dimensional manifold in the configuration space of my hand, right? And so if we can sort of capture the synergies between the different degrees of freedom, we may be able to solve this by finding a low-dimensional manifold in the configuration space that gets me all of the interesting things that I need to do what I want my bat to do, right? And so Kenny and Sharon, they did this, right? They took their bat, they put the bat in a wind tunnel, put markers on it, tracked the markers, solved an inverse kinematics problem to compute the joint angles for the robot. I'm sorry, for the bat as a function of time. Then they did something very much like principal components analysis to find what really are the meaningful motions or the meaningful degrees of freedom. And here's the answer. There are three interesting things that happen when a bat flies. It flaps its wings synchronously. There is an asynchronous motion of the wings that folds them in and out, right? You can fold the wings in and out as you fly. And then there's a tail or a hind limb. And that has to do more with controlling the orientation, right? Similar to what happens in airplanes, if you like. So what does that mean for us? It means what we want to do is design a robot that has the ability to reproduce these three kinds of motion, and it's low weight, low power, small size, structurally stable, etc. Right? So what you see on the right of this image is the final design, right? But this is not what comes out of thinking about what's on this slide, right? What you see as the final design is what comes out after a bunch of optimization that I'll talk a little bit about. But step one is figure out something about the topological structure of the robot, and step two is optimize that stuff, right? So the topological structure that you see here, right? There are parallel mechanisms in each wing, for example. That is the product of Alireza Ramazani, who's a very clever, he's a very clever roboticist and control theorist, but at this moment he was a very clever designer of kinematic mechanisms for us. So once you have the topological structure, then you can do optimization of the kinematic parameters, right? So here's a side view of that structure for one wing. And you have three kinds of things. You have degrees of freedom that are actuated, meaning they're connected to motors. There are three of those. They're shown in red. You have 3 degrees of freedom that are not actuated, that respond passively to the other degrees of freedom. And then you have a lot of fixed kinematic parameters, which are very similar, excuse me, to the parameters that you would use in a Denevit-Hartenberg representation, right? So these are very similar to the DH parameters if this were a robot arm instead of a robot bat. So there are a lot of parameters here. What do? You hypothesize a design for your robot. Once you hypothesize that design, you can push the joints through the trajectories that you collected from the motion capture data, or you can actually optimize the trajectory directly of those joints. But in either case, your simulator for the hypothesized design will tell you the trajectory of the motion capture markers on the robot if you had built it and tried to fly it, right? So we know what the motion capture markers do on the biological bat. We can hypothesize what they do for the designed robot bat. And the trick is to try and get the performance to match from our optimized system to the biological system, right? And we do that by collecting data, doing principal components analysis, and minimizing a Frobenius norm between the two data matrices, right? So that's basically how that all happens, and that's not the point of this talk, right? For this talk, it's just enough to know that you can do an optimization to converge to an optimal design. And if you do that, you arrive to a design of the kinematic structure and a trajectory of the joints that looks like the thing on the left, right? The thing on the left, B2, is the bat. The thing on the right is the biological robot. And to your eye, my guess is it looks like those things are the same, right? The trajectories look the same. The geometry looks the same. Everything looks pretty good. And that bat won't fly, right? If you build that bat and toss it into the air, it will crash to the ground. And there are a number of reasons for that. One of them is this. All of the optimization that we did was based on geometry. And I think I don't know that we actually made a bet for money, but I was really sure at the beginning of this project we would be able to reduce the problem of flapping flight to a purely geometric problem. And I was wrong about that. There's no force, no torque available in the biological bat data set. So there's no way we were going to optimize for that kind of stuff anyway, since we didn't have any ground truth data. I didn't believe we would need to, but it turns out we did. There are really significant differences in the dynamic properties of the robot that we built and the biological animal, right? The inertial parameters are really different. Our robot bat is heaviest where the battery is, and biological bats don't have that problem, right? Biological bats are more or less uniform weight throughout their body. The membrane on the wing, we used a silicon membrane that was quite deformable and more deformable than the wing of the biological bat. And then there's nothing anywhere in anything to this moment in the talk explicitly about aerodynamics, right? So we didn't do anything to capture aerodynamic forces. So all of that work that we did to design that bat, which I thought was quite beautiful and I was quite proud of, failed to produce a flying robot for these reasons. But that's not really a problem for us because mechanical engineers and aeronautical engineers, they have models for all the things that are missing from the data in the list above, right? So what did we do at this point? We wrote down a model. So here's the configuration space of the bat. You need 6 degrees of freedom for a body attached frame. And then you've got passive joints and active joints, right? So that's the whole configuration space. You can write down the dynamic equations. It's just the usual Lagrange-Euler equations plus an aerodynamic term. You can do a little bit of rewriting and solve for the accelerations as a set of unactuated accelerations and a set of actuated accelerations, right? So you have the unactuated dynamics and the actuated dynamics. And the unactuated dynamics are the things that you cannot control directly. And so there is no, for example, there's no actuator on the robot that changes the Z coordinate of the robot's body attached frame, right? You have to actuate the wings and hope the aerodynamics lift the body in the air if you want to change the Z coordinate, right? So there's a bunch of what's happening that you have no direct control over through the actuators of the system. And those are the things in this psi set of equations at the top. The actuated dynamics at the bottom actually are the sort of bread and butter for roboticists, and we know how to use those. This is the tricky part, right? There are aerodynamic forces that happen here. And the aerodynamic forces are not friendly in any way. Then if you take away the aerodynamic forces, you're left with the usual Euler-Lagrange equations. And the immediate property, the thing that jumps out at you as being super nice, is that everything on the right-hand side is independent of everything on the left-hand side. At the moment you add aerodynamics, that's no longer true because the aerodynamic forces depend on things like the wing speed, right? So the configuration variables and the state variables are directly related to what's happening with the aerodynamic forces. And so you can't do the usual kind of nice decoupling inverse dynamic control, for example, that you might do for a purely mechanical system. So what did we do? We used really a simple model for aerodynamics, right? Maybe the only thing simpler than this is to model the aerodynamics as there are no aerodynamics, right? Just to model it as a brick or as a potato or something. This model says the two wings of the robot, we will treat them as rigid planes. All right, and so it's a rigid polygon, in this case rectangle, that moves through the air, and as it does, it generates forces that are characterized by lift and drag coefficients, right? So it's the most basic kind of aerodynamics that you could see, but the lift and drag coordinates depend on the velocity, right? So the forces that are exerted do depend on the velocities, but in this case, in a pretty simplistic way. The nice thing about this model is that it's super easy to evaluate just by doing integrals along strips of the wing, right? So you take the wing and you decompose it into strips and you integrate along those, and it's not difficult to get the answers back quickly to simulate this in a forward simulator. And once you have that, you have a model for everything. You can do trajectory design. So let me call the desired trajectory R sub D, parameterize it by some set of parameters that I'll call beta, which might include the flapping frequency, the amplitude of the wing flapping, the wing folding parameters, etc. I can write down the tracking error and differentiate it twice. And the reason I differentiate it a couple of times is to basically smooth out numerical problems in the numerical computations and optimizations. And when I do that and substitute the error equations into the dynamics, I arrive to an aerodynamics equation that you see on the bottom of this page. Right, so you tell me the desired trajectory, and here's the trajectory for the actuated joints Q sub A. So these are all the equations that we have now. Right, we've got the aerodynamics at the bottom, the full system dynamics at the top. That is a forward model. Right. If you tell me the desired trajectory, I can solve these equations basically from the bottom to the top and compute what the unactuated dynamics will do. Right. So I don't have direct control over the unactuated dynamics. And in fact, I have to solve a couple of sets of equations even to know what they're going to be doing. But I've got a way to do that. And that means I can do optimization. And this is how we do it. Right. So we just we optimize, first of all, to ensure some periodic motion in some of the coordinates, particularly the flapping coordinates. We want stability. We want to make sure that you don't fall out of the sky. You don't do rolling or pitching. Yaw is not particularly good, but it doesn't have the same instability properties as pitching does, for example. We want to minimize the expected energy, or the expended energy, rather. And we can do all of that just by using a shooting-based method optimizer. And we used fmin_con to do all of this, right? And how do you do that? You numerically integrate the dynamics forward, you numerically calculate a gradient of the objective function, and you iterate on that until you arrive to a trajectory. And if you do that this is a reduced order model that we worked with, this is the kind of trajectory that comes out. And this is a pretty good trajectory. Aerodynamics are here, but considered only using the simple aerodynamic model. The last question is, how are you going to control that thing? And the answer is, it's not the topic of this talk. I'll just say we use these Poincaré sections, and we linearize the Poincaré map, because really the only time it makes sense to exert a change in control input is either at the bottom of a wing stroke or the top of a wing stroke. We did it at the bottom of the downstroke. The thing that's important is we take that Poincaré map and we linearize it. And when you linearize it, it looks like this. And the only reason I'm showing you this equation is because if you've had a first control theory class, you recognize it as being the linearized dynamics of a dynamical system, right? These are not strange equations to a control theorist. We know how to solve it. It's a linear system. And in fact, that's what we did. Right? We used an LQR approach to design an optimal controller about the linearized ideal trajectory. And there's the bat flying in the Urbana-Champaign stock pavilion. And we're happy with that, right? If you let me show it to you again. This is Alireza tossing the bat. He is incredibly skilled at matching the initial conditions of flight to the linearized trajectory that was ideal, the idealized linearized trajectory that we used. And what can we say looking back on that long experience? It was a 3-year journey, maybe even a 4-year journey through this robotics design and test problem. What are the lessons? So the first lesson is this: collecting data for a biological bat is hard. It's hard for a lot of reasons. One of the reasons is it's an animal. You have to convince the animal to do the thing that you want to measure. And bats don't wake up in the morning dreaming of flying in a wind tunnel. So you have to convince them to fly in the wind tunnel with data markers on them, with motion capture markers on them. Some of the data that you want, you can't have, right? So there's no force and torque data. That's off the table for you. And it's expensive and time consuming to collect data on the robot bat, right? So the robot bat, I mean, you saw it, we could throw it, but if you noticed, the experiment that I showed you was in this giant stock pavilion. There's no motion capture system in there, right? That's completely off the table for us. The expense of equipping that with motion capture is far too high. So there's no ground truth data available for long flights. The only ground truth data we had available was for very short flights in the motion capture room. And it's hard to analyze steady state long-term behavior over short trajectories. Every time the robot hit the ground, there was a pretty good chance that a piece of it would break. It was all 3D printed stuff. When something broke, it had to be replaced and glued back together, and it takes hours for the glue to cure. So the expense of repairing the bat robot, it's not that it costs so much money for new 3D printed parts, it's that the students and the postdocs working on the project just have to sit around and wait until the glue dries, which means come back tomorrow. Right? So every time the robot breaks, you're done for the 24-hour period, basically. What did we learn on the model-based side? Well, at the moment you have models, you can do optimization, and we did a bunch of optimization in this project. Right? We optimized the kinematic design, we optimized the trajectory for the geometric aspects of the flapping flight performance. We optimized the trajectory again using dynamics and in particular aerodynamics. And then we optimized control gains by linearizing a model. Right? So we did 4 different kinds of optimization using different kinds of models. And what do we learn? Closed loop control makes that bat fly pretty well, even when the models are pretty stupid. Right? The Dickinson aerodynamics model is really not remotely accurate for this bat robot. Right? The bat robot, we used this silicon membrane that we fabricated ourselves, and it was very flexible. In some talks, I talk about the sort of power amplification that you get. It's like an analog power amplifier of aerodynamics. It's like a spring in a leg when you put a flexible membrane on a wing, right? During the downstroke, the membrane deforms and fills up with air, and at the bottom, it pushes the air out to lift you back up. And we didn't model any of that, but the closed loop control worked really well. Another thing that we learned, which any control theorist already knew, if you're doing a bunch of linearization, when you get away from the nominal trajectory, things break. And so I made a mention of Alireza being able to throw the bat robot just right, because if you've linearized to design your controller about a particular desired trajectory, then you need to be sure that at the beginning of the flight, the robot's trajectory matches the initial conditions of your linearization. So this is something about the limits of models. So limits of data on the top, all the cool stuff we can do with models and control in the middle, limitations of models on the bottom. Right? And that's the sort of overview of what we learned about models and data from the BAT project. Here's the second example. that I'll talk about. It's vision-based control of continuum, soft continuum arms. Soft continuum robots, you may have seen robots like this. They are often biologically inspired. In the case that I'm going to talk about today, it's a robot that you can essentially think of as a long, flexible tube that can be actuated somehow. And the particular robot that I'm going to talk about today was designed by my colleague Girish Krishnan at the University of Illinois, and it's very cool. If you take a rubber hose and wrap string around it, and then you go back and wrap string around it at another wrapping pattern. So you have two patterns of string being wrapped around. Then you inflate the hose by pumping air into it. What the hose does depends on how the strings are wrapped, right? So you can see two examples on the left, a particular kind of crossing angle that causes the mechanism to extend or contract when you change the air pressure. And at the bottom, you see a wrapping pattern that causes the mechanism to rotate. And then on the far right, you see a video that shows this robot moving around. And the only thing that's causing it to move is changing the air pressure in 3 rubber tubes, or 3 flexible tubes. I'm not sure they're rubber. Right. Each one of them has a distinct wrapping pattern, so you can think of them as forming a kind of basis in the vector space of motions available to this robot, right, in its otherwise infinite dimensional configuration space. How do you model that? Well, the way you model that is you put a spine through the robot from start to end, and you characterize what's happening at each point along the spine, right? So you define a coordinate system. It's just the usual kind of frame that you may have seen in a differential geometry class. You have a position along the curve, an orientation at each point on the curve. You have the overall length of the robot being parameterized by some distance parameter S, and you have stretching and shearing. So Q here, Q is stretching and shearing strains. Q is not configuration. And I've just realized for the first time, this is a bad choice of notation for a talk that uses configuration space a lot. So keep track of the fact that for now, Q is about stretching and shearing. Kappa is about bending and twisting. So for this robot, stretching in the x-axis is the only kind of stretching and shearing that we can have, right? We don't have any way to like stretch things perpendicular to the spine, for example. And these are the equations of shape, right? It's basically an ordinary differential equation along the length of the curve that defines the shape of the robot. So if we take those equations, how are we going to actually talk about the robot as a robot, as opposed to looking at the point-wise description of the geometry of the robot? There are a bunch of different ways to do that. Some people model as constant curvature, some with piecewise constant curvature, etc. We chose to use the Couserot rod model. Here it is. It looks sophisticated, but it's really straightforward. You got a stiffness matrix, pre-strains, actuation input, actuation moments, external force on the tip, gravitational force. It's a pretty intricate model, but everything makes intuitive sense, right? At least in terms of understanding what the individual components are. You may not understand immediately why the components show up in the equation in this way, but it's easy to understand what's happening in terms of the individual components and what they mean. So if you want to do visual servoing for a robot like that, you put a camera someplace, either on the end of the robot or you mount the camera in the world, right? You look at the tip of the robot and you see an image. And then if you change the input a little bit, meaning you compute U dot, right, the differential input, that causes some change in the configuration of the robot, right, in the end effector frame. If you're looking at differential changes at the input, what you're looking at the output is differential changes in the output, which you can characterize by angular and linear velocities. And there's a Jacobian matrix that relates those things. And then there's one more Jacobian matrix, or interaction matrix, we call it, that relates a change in the position of the tip of the robot to a change in the image of the robot, right? So that's the matrix L, G, and the adjoint operator is just doing a coordinate transformation to make everything appear in the right coordinate systems. And you can do this whether the camera is mounted in the world or whether the camera is fixed on the end of the robot. That's the forward model for the system. If you want to control the system, you work backwards, right? Here's the error in the image. You go backwards by doing a pseudo-inverse computation, which essentially tells you what should be the differential control input to reduce the error, right? So this is just proportional gain, basically, on a linearized system. And again, you can do the same for the camera mounted on the ceiling or the camera mounted on the end of the robot. The trick here is the Jacobian matrix J. What is the relationship between a change in the input pressure and the angular and linear velocities of the end effector? Well, this is not what this talk is about. You can solve some differential equations and arrive to something that looks like this, right? This is a numerical algorithm waiting to be implemented to compute the Jacobian at the tip of the robot, right? You've got boundary value conditions that you have to match, but you can solve this. And so you've got essentially now a model that comes from taking the Cosrock-Rod equation and doing a bit of manipulation. It takes into account some material properties and some external forces, and you can generalize this to any soft continuum arm that you like, as long as you know the geometric and inertial and elastic properties of the robot under consideration. And now I'll show you some experiments if we use that method to control the robot. So we put a camera on the end of the robot, which you can see in the left image. What I'm going to show you is the view from the base camera, the view from the tip camera as the robot moves in its environment, which is shown on the right. And so here's the first example. It's not that interesting. As you expect, the robot tracks the trajectory. You show it a target point, and using vision-based control, it's able to get to the target point. And it traces out a trajectory that looks like this, which is pretty close to optimal in the image space. You can also show that this is going to be robust to disturbance, right? It's a closed-loop controller. So there you saw my student Ali drop a weight on the robot, and you see that it recovers pretty quickly when the weight is removed or attached and converges to the goal position. Here's an example where Ali actually ties a string to the robot and pulls it, right, to try and pull it away from the goal. And you see the robot fighting back using vision-based control to get to the goal. So it's pretty robust to, at least I'll say, to friendly external disturbance. I'm not sure that Dr. Al-Baladi was all that aggressive when he was applying those external forces. You can also take these robots and cascade them. So here's two of them connected in series. If you've got two connected in series, now you've got more degrees of freedom to play with, and you can do things like track two targets at the same time. Excuse me. And so here you see the robot trying to bring the blue circle to the blue dot, green circle to the green dot. And not surprisingly, it succeeds, right? And what did we learn? First thing that you learn is it's difficult to simulate this system well enough to learn how to map visual imagery to control inputs, right? Sometimes in the robot world, people talk about pixel to torque. In our case, it would be pixel to air pressure going into the robots. It's really hard to simulate these robots at that level of precision. So we're not able to do that kind of learning. But again, we learned that a reasonable model, and the Cosrock-Rod model it's a pretty reasonable model, but certainly it's not true. Right? There are some very weird discrete effects that happen along the length of that robot because of these winding patterns of string. And yet the model, together with a closed loop feedback controller using vision, gives very good performance. It's easy to update everything in the model over time as the robot ages. There are explicit ways in the model to account for external forces. Even though we just treated them as disturbance, you don't have to. You can estimate them and deal with them. And it generalizes very well. It's possible to do data-driven methods with this robot. In fact, there's a chunk of Ali's thesis using data-driven methods to do essentially a machine learning approach for the interaction matrix of the vision system part of things, right? Which basically just corresponds to learning a constant mapping from things happening in the image to things happening in the 3D world, right? So that is the sort of thing that visual servo people have known about for a while, that you can do that. So you can do that. Here's the third example. It's a graffiti robot, right? So this is a cable-driven robot. It's parallel. Let me show you how it works. There's the robot in the lab. It's got 4 cables, 4 motors that drive the cables, some sort of end effector that holds a can of spray paint. And here you can see where the cables are as the robot moves around and does its painting. This is what the block diagram of that system looks like. So it's a pretty high level model. I haven't shown you anything about what's inside the dynamics, right? There's some system dynamics called F. There's some observation function. There's an estimate called X hat, etc. The point of this part of the talk is to say every one of these pieces, because it's a discrete time system, we can implement using factor graphs. And at the moment you can do factor graphs, you have at your disposal a way to do very quickly optimization over all the things that you might want to optimize, right? And in this case, the graph is quite sparse, and so the methods are quite efficient. I'm going to show you 2 results, right? This is the time optimal control, which is a bang solution. It's not surprising. And then there's a quadratic objective control, and the objectives are shown at the bottom, right? And the reason to show you this is to say, if you've got a model, you can do optimization, and if you can do optimization, you can swap your performance functional for whatever you like. And so here you see 2 results. On the left is the time optimal control, and on the right is a control that minimizes this thing that's shown at the bottom, right? So there's a term in the performance functional that penalizes for putting high tension on the object, because high tension causes bad performance basically when the tension gets too high at a high level. And so what you can see is that time optimal control is faster, but also the star is not as pretty, right? The lines are not as straight. So if you're willing to reformulate your performance objectives, you can get much better output in terms of how it looks, but it takes you longer to do it, right? And so model-based approaches allow you to do that kind of thing. What can you do with data? Well, the kind of data that's available for this kind of system is data from humans. And so we've had a lot of interaction with people. On the left is a real graffiti artist. I think he's from the Netherlands, who was in Atlanta, and we did motion capture on this dude while he painted the alphabet. And so we have his full font set, right? His whole graffiti font set is something we learned using motion capture data. And we frequently go into the field and let people play with basically doing teleoperation using an iPad to drive this around to do their own graffiti. So there's a lot of data that we could use on the front end to sort of create interesting trajectories, but everything about the robot itself is model-based. And part of that is because we understand the model pretty well. I mean, these parallel cable-driven robots, we know how to write down the equations and model them. There's not a huge need for learning about that system, right? And that's basically what this says. Oops, too far. Go back. And again, reasonable models feedback control gives you pretty good performance. In this case, the trick for feedback control is that it should be fast. We learned, and well, actually Jerry learned, high bandwidth feedback control really makes this system perform very well, even with unknown loads at the end effector. As you paint, the weight of the paint can changes over time. So there's that. It's 2:28. Let me take 5 minutes to show you one last example. This is a safe human-robot interaction. And a lot of this is the work of some of my students, Mohammed Murtaza and Sergio Aguilera. Both of those guys have graduated and gone into the real world now. What do I want to say about this? The robot that you just saw is a KUKA robot, and we know everything there is to know, right? We know the dynamics of that robot. The kinematic parameters are well known. The inertial parameters are known to KUKA, so you have to estimate them yourself if you're in your own lab, but you can. So what are we going to do? We're going to use control Lyapunov functions to get performance guarantees, and we're going to use control barrier functions to get safety guarantees. And we're going to describe all of these out in the task space, which means what? You take the differential kinematics of the robot, you can express those in the task space. You can take the Euler-Lagrange equations, solve them, and come up with the operational space dynamics, which basically means what are the dynamics out with respect to the end effector instead of what are the dynamics of the joint torques, or at the joint torque level. And you can rewrite this in the usual affine form, and now it's a control problem that we know how to deal with using control Lyapunov functions and control barrier functions. Right, so inverse dynamics, we know how to solve that as well, right? You just invert the dynamic equations in the task space. And if you know this, it'll make you feel good. And if you don't, I don't have time to teach you today. And here's the basic approach. I'm going to model all the obstacles in the world by ellipsoids. That's how I'm going to define my barrier functions. Safe sets look like this, right? It's just an ellipsoid. A is a positive definite matrix in the middle. Differentiate that thing until the input appears. It's a relative degree 2 system. That's the equation on the bottom. The L's are Lie derivatives. Doesn't matter much here. What matters is you can eventually arrive to a situation that has to be satisfied. And it's this red condition, right? That a certain combination of derivatives of the function h have to satisfy this inequality. And now you have a constrained optimization problem, right? I could, for example, minimize the distance to the desired trajectory subject to the constraint of the control barrier function, meaning I don't hit anything. This nominal trajectory is something I probably won't have time to talk about, but you can use this for all kinds of stuff. You can do collision avoidance, maintain the orientation of an object, maintain a fixed relationship to a moving object. And control barrier functions, I'm not trying to sell them as the solution to all problems, but they're handy and they're easy to use, they're modular, and they're easy to work with theoretically to actually prove things. So you do the same thing with control Lyapunov functions. And again, none of these equations are super important. What's important is, in the end, you come up with a condition such that if your dynamics satisfy this condition, you win. Your system is stable, right? And that's the condition that we care about. And that means I can now do all kinds of stuff as a constrained optimization problem. So here, let me just minimize something. For example, deviation from a nominal control input, subject to system dynamics, safety, exponential stability, and whatever else you like. Right. So this is a purely model-based approach that admits a constrained optimization solution. And here's some results. Right, this is just the robot following an ellipsoid trajectory. And in a minute, we'll turn on the constraints that you see. That's an obstacle now. And you see how the system performs when you tell it there's an obstacle in those rectangular blocks. And I'm running a bit low on time. So yeah, I'll just skip ahead. You can take that same idea and wrap one more level around the outside in this hierarchical kind of controller to generate optimal trajectories for things like pushing non-holonomic vehicles. And so here is a mobile manipulator pushing a cart with an unknown load. You estimate the load using extended Kalman filter if you like. There's a penalty for moving the hand on the grip as you push the cart, and you just saw it stop and move its hand because there was some moment where it became better to do that than to exert increasing torque on the wrist. And you can track trajectories pretty well using all of this. And here's physical human-robot interaction. That's Sergio. He puts a couple of bottles of water on the robot. And using the low-level control where the barrier functions are enforcing, in this case, orientation of the end effector, And the control the up and off function stuff is implementing an impedance-based controller. You can move this thing around pretty easily while enforcing the constraint that you never spill the water. Right. And I thought he would be more aggressive, but maybe I thought he was going to bounce it a little bit, but maybe not. It's a little better, but it's the robot that he's playing with, right, by doing these things could kill him, right? I mean, it's a KUKA robot with a 14-kilogram payload on a mobile manipulator. He might be able to outrun the mobile manipulator, but I don't know if he could. So this is a dangerous system that he's made into a friendly, like a puppy dog almost. And what do you learn? High fidelity models exist for everything in this system. So we can get safety guarantees, stability, optimization-based methods, feedback linearization, all the things roboticists like. But hidden inside this system is essentially a machine learning approach to estimate the inertial parameters of the cart if you're doing cart pushing, right? So at the moment you start interacting with the world, there are things that are not modeled well that you don't know about, right? And in our case, we put a 10-kilogram ball in the cart and let it roll around, things like this. We have safety guarantees, but they're only as good as the vision system, right? Because our safety guarantees that you didn't see with Sergio interacting with the robot and the robot not hitting him is coming from a computer vision system, finding the people in real time. But big data has basically solved the vision problem in terms of tracking humans in reasonable settings, right? So we use YOLO. I don't remember which version we used, and it's remarkable. It's robust and effective and fast. So what's the message here? If you have good models, exploit them. If you've got solutions you can get from the machine learning world, like for the vision part of the system, you should use that. And I'm going to stop there because I'm already at 2:35 my time, which is 5 minutes past the end of this talk, I think. And these are the take-home message, right? Good models, you can do optimization. Reasonable models plus feedback. Every time that I've used that approach, I've gotten pretty good performance. If you have good model-based methods, you have the possibility to give guarantees to the users, right? There are components of robotic systems now that came from the machine learning world that I, as an old-fashioned model-based robotics guy, trust enough to just use them, and particularly in some of the computer vision components. And then lastly, out of distribution errors take different forms for the control theorist than for the machine learning person, right? So if you're doing machine learning out of distribution errors, it means I've seen problems that weren't in my initial distribution of problems that I did the training on. The analogous problem for the model-based learning people is, for example, I did linearization and my system was too far away, and so the linearization broke down, right? It's not exactly the same problem, but there's a really nice analogy between those two things, where in one case, you find the limits of your training set, and in the other case, you find the limits of your model. I think I'll stop with this sentence, that the next decade will be filled with people doing interesting work, integrating machine learning with model-based approaches. People are already integrating those things, but right now it tends to be machine learning people using some control theory or control theorists using some machine learning stuff. And so the real genuine interaction between the two, that's still pretty young. So I think there's a lot of work that will be done in the coming years that will be very interesting along those lines. And I will stop there, I think. Yes, I will stop there. And give the seminar back to you, and we'll do whatever you like now.
So for the presentation was really interesting. Are there any questions for Dr. Seth? No? Okay. Thank you, Dr. Seth, for your time. And we wait for us the next weekend. Thank you.
Thank you, Seth. See you soon, I hope.
I hope so too. Maybe I'll see you at ICRA this year.
Maybe, hopefully.
I hope so. All right. See you
Thank
all.
you very much.